So we have the midterm next Monday. I've written it and I hope it's easier. If you do last year's midterm, it should be similar. No tricks this time, I promise. And I'll go over a review on Thursday for this midterm two, and so that'll be on Thursday. And then in class, people are going to take it on Monday. People who are online will it'll be available to you on Sunday through Tuesday. And I think there are a few people who have reached out for midterm one, but are not or are not going to take it online on midterm two. So just reach out to me just to be safe if you are one of those people who actually do need to take it online but haven't reached out to me. You can tell if you are an online section or not online section, but have the online midterm if it's assigned to you. So it'll pop up under quizzes. But if you don't see midterm two under quizzes, then you don't have it assigned to you. So reach out to me if you cannot take it in person. All the material covered from today forward will not be on midterm two. And I think so we'll be covered anything up to PD, PI, PID, lead and lag, but not lag lead. Lag lead will not be on the midterm. I'll be honest with you, I will not have PID on the midterm as well. It'll either be PD or PI or lag or lead on the midterm, but I'm not going to have a whole design question. So you don't have to worry about designing a PID controller. One other thing about this week's homework too, that's due. While it's not going to be the lag lead design isn't part of the midterm, the concepts using lag lead design is helpful with angle magnitude criterion. Those are good concepts to know for midterm two. Drawing the root locus and steady state error, those are all good concepts. Like lag lead is a good uh, problem that covers basically chapters 7 through 9, I think. Steady state error is starting in chapter 7. There's not going to be much material on stability because we didn't cover much on stability, so that's also okay. Like you don't need to know Routh. So on last year's midterm, I do have a problem on Routh-Hurwitz criterion. You don't need to know about that. And finally, one last comment about the homework is that when you're doing your PID controller design or your lag lead controller design and you're trying to design it for peak time that a reduction of a peak time, but you actually get a really long peak time, that's that's common. You don't have to because it's an approximation, it doesn't always work out. And let's say you're shooting for 1.3 second peak time and you get a 20-second peak time. That's actually normal. And it has to do with this little thing I drew last week, this little green line where we have this local peak, but that's not actually the maximum value. In MATLAB, when it's looking at the peak value, it's looking at the maximum value your response attains. So it's going to ignore this like local peak. So your peak time calculation might not be correct, and that's okay. Because in reality, like when we have the PI controller, it might look something like this, like that's like a PD controller without PI. But then once we add a PI component, these are PI components, or this is your PID and this is your PD controller. You can see that it's going to take like some value here or some value here as your peak time instead versus TP here. One other thing about the notes I have here too is that I have uploaded these notes, so they're not complete, but I will finish them today. So, but regardless, these have been uploaded, the incomplete version. And the only thing left to do is to finish this lag lead compensation example. Are there any questions before we get started? Okay, so and actually looking ahead with the schedule, so we have the midterm Monday, and then you'll still have a homework due next Thursday. It's going to be a really light homework. And then I think looking forward, I don't think online people will be able to see this, but looking forward, we have next week, we only have basically three classes besides the midterm. So Tuesday through Thursday. And then the week after, we have Thanksgiving break. So we only have class Monday through Wednesday. I know people tend to travel a lot during that week, so if you want to attend online, that's completely fine. Um, we basically just have 2 more weeks to cover chapter 10. So chapter 10 is going to be a similar length as chapter 9, and we're probably going to go into midweek of December, finishing up chapter 10. Chapter 10 is going to be on Bode plots and Nyquist stability criterion. I'm currently writing up the lecture for chapter 10 into two parts now. Um, I have uploaded part one of chapter 10, and then I'm gonna have part two of chapter 10 uploaded sometime next week. Apologies for taking so long on that. And then we have the final on December 9th. What I'm going to do during the last week of class is probably like the last 2 days of class, I'll have like a big review of everything we've covered. But we actually do not have that much more time, despite it being a month away. The time will fly pretty fast. So that's the schedule. And during Thanksgiving, there's going to be no homework due that week as well. So no homework due on the 28th. Just enjoy your holidays. Um, and then the last homework will be due on the 5th, December 5th. All right. We're gonna start lag lead. So last class we designed a PID controller, and this week we're going to wrap up this chapter with lag lead compensation design. And basically, what we're trying to do here is we're trying to reduce the settling time by half for, while maintaining 20% overshoot and having 1/10 of the uncompensated steady state error. So this is what I mean by this. Lag lead compensation is a really good example that tests your concepts for midterm 2. This is going to be from chapter 7. And this is, I mean, these are from chapter 4, second order approximations, um, but then we're going to be using root locus, which is going to be chapter 8, like root locus techniques. And then the lag lead compensation is chapter 9. So it's a really good example problem to go over. So we found that this is a type 1 system, meaning that we have a steady state error for a rampant input. And basically, we wanted to design the first step is to design a lead compensator. So we're going to use second order approximation. To estimate our system performance. So it's nothing new that we've always used second order approximation for our PI or our PD controller design, and it's the same with the lead compensator design. And we're going to use the equation where percent overshoot is 20%. So that our damping ratio is going to be equal to minus ln of 20/100 divided by square root of pi squared plus ln squared of 20/100 squared. And we get 0.456. So using second order approximation, we can see that Well, yeah. So we're gonna use second order approximation to locate our uncompensated complex poles. I guess in this step here, I just use MATLAB. So using MATLAB, so our locus, we're gonna find poles at zeta is equal to 0.456. So we find them that the complex poles are at it's going to be at minus 1.79. Yeah.
Our locus, is there a better way than just clicking on the graph?
I wish I had a better way. Yeah. No, I don't have a better way. Yeah.
On the graph, are you using rlog find, like the command?
Oh, our loc find. Is there a command for that?
I just do rlocus and I try clicking on the rlocus graph. It just gives me like the x and y coordinates. It doesn't give me all the information. So I have to
Oh. Oh, I see. So one thing you can do instead, well, this I don't know if this is going to be easier. Let me just write this down. Uh, is that when you're tr taking the closed loop transfer function here, and actually I'm not exactly sure how you would do this, but maybe this is going to be a little tangent. This question is like, how would I use our, or is there a better way of using our, better method of finding the complex poles than using our locus? So the another way I can think of is if we actually take the actual closed loop transfer function. So it's going to be kg over 1 plus kgh, or 1 plus kg. And when we work that out, we get this form here. That's going to be k over s cubed plus, oh no, 16s squared plus 60s plus k. Is that correct? I think we're good. Yeah, I want to say we're good. That's a closed loop transfer function form. Will you give us the complex pole location? For designing compensators and exams, will you give us the complex pole locations? Yes, I will. Or, uh, okay, so I guess my answer kind of tells you if I will or will not. My exams for lag, lead, PD, or PI will all be second order systems. So when you design it, it's not a second order approximation, it is a second order system. So the uncompensated system is going to be a second order system. So when you do look for the complex poles and zeros, you don't have to use our locus. You can just use second order form. I hope that answers your question. Um, yeah, so let me get back to your question, but do you have another question on top of that?
the function rlog find, and you can actually get like if you do the brackets.
So so if I do the brackets of R log find, is that what it looks like?
Bracket, find the k, the gain, and then
Gain. So gain and then
in brackets, and then
poles.
put this.
Oh, I see, I see. So I say K poles is equal to R log find, like that.
Sorry, trying to figure out the input because it's R find in like the system and then some vector key.
Okay. Um, maybe what I'll do is I'm going to sorry, online folks. I'm just Googling this real quick. Perfect. All right, I'll say form question. Help. You could start with this. Our log find. Oh, okay. So then we have K poles and of our system.
Just put in the system.
It then takes a vector of P. So I'll look into this. But maybe to answer your question, because maybe there is a more effective way of finding this than just clicking and dragging. I just never looked it up because I don't use it. I don't think people really use this, but the more of the highlight is what I'm trying to show you in this chapter is what root locus is to describe to you how a system behaves. And then I just use our locus just for this class pretty much exclusively. I do think our loc find that probably will be easier if I expand into the documentation. But I don't want to like speculate because it might be wrong. So I'd rather come back with the correct answer. But to actually answer your question though about complex conjugate poles, uh, one thing about this form, and if I were to draw the root locus of this really fast, uh, I know that we have a pole at the origin, a pole at -6, and a pole at -10. So our root locus is going to look something like this. It's going to look like, so we follow the real axis segment rules. And then we have a breakaway point with asymptotes at 60, -60 degrees, and 180 degrees. So that's our root locus. So we know that there's always going to be a real pole and a pair of complex conjugate poles using my root locus here. So then if I were to rewrite this equation, it would just be like this. It would be like K divided by S plus, maybe I'll say A, divided by S squared plus 2 zeta omega n S plus omega n squared. And so from there, because just from my root locus, I can see that I have a third pole that's real and a pair of complex conjugate poles that are um that will have where I have zeta is equal to 0.456. So I need to somehow factorize this and get that form. And I think that's the most difficult part of this problem. And and to be quite honest, I actually do not have a good answer for that. So at the end of the day, I'm sorry. uh I'm sorry. Um I won't be able to, I can't give you a perfect answer. So that's like the most I can think of. And then maybe we just want to sweep K until we can get this form, but I'm not quite sure how to get there. There probably is a way to, and I'm pretty sure if I really wanted to, we can you can write a function to do that because this is equal to negative zeta omega n um plus or minus omega n times 1 minus zeta squared. And if you were to write a function, you can determine on the root locus, because this is like a ratio of your length and width on the imaginary axis, like on the real axis and the imaginary axis. So then you can write a function that searches for this ratio with this corresponding damping ratio, because this is like where damping ratios are constant. Zeta is equal to 0.456. You can write a script that looks for this intersection point. That's probably going to be zeta is equal to 0.1. And then this is like zeta is equal to 0.9. So those lines are going to be constant. It's going to be the same across all root locus plots. Um, yeah. The thing is that even if you don't get these exact values, if you use minus 1.9 or minus 1.7, it actually doesn't matter because this is a second order approximation. Um, at the end of the day, I'll show you all actually how we do PID tuning, and it's none of this calculation stuff. Anyway, so I guess I didn't really answer your question, but hopefully that I don't know. I I'll look into our loc find, or maybe if you want to look into it for me, that would be great. But that sounds okay. Thank you. That sounds like it sounds promising. Just for so from the root locus though, if I were to choose this point here, 1.79 plus 3.5, I get a gain of 192 and a damping ratio of 0.456. Um, so then using second order approximation, um, a TSU is going to be floor divided by zeta omega n. I'm calling this omega nu, which is for the uncompensated system. And I get 4 over 1.79, which is equal to 2.32 seconds. And to get our compensated settling time, it's going to be 1/2 of the uncompensated settling time, which is 1.12 seconds. And we want this at zeta is equal to 0.456. Well, this is a long example. Maybe we won't get to chapter 10. Okay. So basically, lead compensator design, we get this uncompensated settling time, then we calculate the settling compensated time. From that, we can then find the new pole location. And to find a new pole location, we just need to find the natural frequency of the new pole. Right.
It's like so small.
What?
Could be 1.16.
1.16, probably. Yeah. Let's do that. Did I write this correctly? Oh no. Oh, it's yeah. Yeah. Thank you. That is correct. Whenever I get a correction like that, it scares me because I've been giving the same example for the last 3 years. This is the fourth year I'm giving the same example. And if I'm getting corrected on my fourth year, I'm like, oh no, this is bad. It's like there's a moment of panic in my head. Okay, so now we're gonna find the lead compensator pole location. All right. TS compensator is equal to 4 over zeta omega n c. So zeta 0.456. And we have the compensated time, which is 1.12. So then from that, we can calculate the compensated natural frequency, which is 7.83 radians per second. So then from there, we can determine the compensated pole location, which is minus zeta omega n c plus or minus omega n c times the square root of 1 minus zeta squared, which is equal to minus 3.57 plus or minus 6.97 J. Okay, so From there, we want the root locus to pass through that point. I want so root locus to pass through this point, to pass through here. To pass through here. But for lead design, we want the 0 to be to the right or the pole to be the left. Lead design, we want ZC to be smaller than PC. Okay, this is where the textbook and I will deviate. So you get a richer experience because you now have two different designs if you want to look it up. I think textbook in the 7th edition. I haven't looked in that one in a while. Anyway, we have the imaginary and the real part. So I'm going to draw out the pole 0 map mainly just so I can label my angles. It makes it a little easier to identify the angles. So we have a pole at the origin, pole at -6, pole at -10. Then I'm going to choose PC to be -5. I think in the textbook they choose -6. So ZC is going to be 5. This is minus ZC. And then we're going to determine PC. And I'm going to just put it to the left of the 0. We're trying to determine PC now. So we want to find PC using angle criterion. Okay, so the point we're evaluating is right here at -3.57 plus roughly 7. And put it right there. Plus 6.97. I mean, if you want to use 7, -3.6 plus 7, I'm also okay with that. All this is approximation. You can just round up to an easier number if you don't want to deal with it. So I'm going to now define all my angles. So yeah, textbook uses pole 0 cancellation here. So putting the 0 at -6 makes it such that there are 2 less angles to calculate, which makes it a lot easier. You're welcome to do that on your homework. So we have theta 1, we have phi1, theta 2. Sorry, I'm gonna close the chat box here. Theta 3 for the pole at -10, and then theta 4 for our mystery pole. So we have 1, 0, 4 poles, and we're going to use the angle criterion. So 2i plus 1 multiplied by 180 degrees is equal to the sum of the angles of the zeros minus the sum of the angles of the poles, which is equal to phi1 minus theta 1 plus theta 2 plus theta 3 plus theta 4. So now that we have that, we just gotta find our angles. Let's find the angle to 0. phi1 is equal to arctan of 6.97 divided by -3.57, which is our evaluated location, minus the pole location. So it's going to be -5. So -5, so that's +5. And you get 78.4 degrees. Notice that's a quadrant 1 angle. So because this point's above us, your angles can only be quadrant 1 or quadrant 2. Okay. theta 1 is going to be arctan of 6.97 divided by minus 3.57 minus 0. So notice again, this is a quadrant 2 angle now. So if your calculator gives you an angle that's in quadrant 4, just add 180 degrees to get it into quadrant 2. So we're going to get 117.1 degrees. Theta 3 is arctan of 6.97 divided by minus 3.57 plus minus 6, so that's plus 6. And I get 70.8 degrees. And theta 4 is equal to the arctan of 6.97 divided by minus 3.57 minus 10, so that's plus 10, and we get 47.3 degrees. Those are our 4 angles. So then now we're trying to find theta 5 or theta 4, which we don't have. And so then we plug this all in. 2i plus 1 times 180 degrees is equal to 78.4 minus 117.1. Oh, I think I mislabeled this. That's going to be theta 2 and theta 3. So 117.1 plus 70.8 plus 47.3 plus theta 4. And so I get 2i plus 1 multiplied by 180 degrees is equal to minus 156.8 minus theta 4. So again, we're trying to aim for quadrant 1 or quadrant 2 angle. In this case, we're only looking for quadrant 1 because phi 1 is a quadrant 1 angle, and we want theta 4 to be a smaller angle than phi 1 because we want to meet this condition. Maybe I'll make a little note here. For this to be true, phi 1 needs to be larger than theta 4. Okay, so let's. Oh, I'm so sorry. There you go. So we're going to just manipulate this equation a little bit to make it a little bit easier to read. Just say theta 4 is equal to 156.8 minus 2i plus 1 multiplied by 180 degrees. Now, oh, there should be a minus sign. Okay, so minus 156.8 minus 2i plus 1. This is an odd multiple of 180 degrees, so we can just choose 180 degrees because that gets us a very small angle. So we choose I is equal to minus 1. Then we get 180 degrees minus 156.8. And we get 23.2 degrees.
Why didn't you just pick 0?
Oh, like right here. If I pick 0, it's minus 156.8 minus 180 degrees, which also works. Actually, it works. Let's say I do choose 0. Then I get, I cannot math, minus 330, 6.8 degrees. That's actually valid because then we're just going about this point to, we're going to this point. and that's going to be minus 330. Well, I shouldn't write minus because we're going this direction now. That's 336.8 degrees now. It's the same angle. So then if we add 100, if we add 360 degrees, because we're just undoing that, maybe I'll do the green here. We get 23.2 degrees, which is this direction now. So they're the same. So you can't choose 0 because at the end of the day, if your angle looks weird, just add 360 until you get to the correct angle. The whole thing about adding 180 is just to flip the quadrants, but they're still mathematically the same because the only difference is if the sign is in the vertical or horizontal component is where you have to be observant of where your angle is going to be quadrant wise. But this angle here, you add 360 to just get it to a positive angle. Usually I like to stick with positive angles, but you don't have to use it. Okay, so now that we have that, we then pick then we can find our pole location. So tan theta 4 is going to be equal to our reference point, which is on the vertical component, which is 6.97 minus the pole location, which is at 0, divided by minus 3.57 minus PC, so that's plus PC. So then we get, when we plug in theta 4, we get 0.4286. Please set your calculators to tan, to degrees and not radians if you're going to plug in degrees. So then from there, when we solve for it, we get that PC is equal to 19.8. So I just want to highlight that if you don't make this condition, you do have to go back and redesign your lead controller. So you had to choose a different 0 location. So I wouldn't even continue on unless your angle was smaller than the 0 angle for your pole. Yeah.
Physically the wheel to add a pole.
What it is that physically mean to add a pole or 0?
You change the code.
I see it as, okay, maybe adding poles, you're increasing, well, that's not physical, but it's all code based for me. So when I increase the number of poles, I'm increasing the resolution of my transfer function. If I have a higher order system, I have more poles, which can represent more individual state variables. And maybe one state variable is going to be on the dynamics of a certain part, or maybe 5 state variables will represent the dynamics of, like, I don't know, a flexible arm. But then I have to add that to, like, I'm looking at like hard disk drives, so maybe I need to capture the dynamics of this little reader on this little disk, but then it's connected to another actuator. So I need the dynamics of that. I need the dynamics of that. So by adding more poles, I can more effectively, or not, it's not effective, but I can more accurately represent that model. So in terms of what it means physically, it doesn't have any physical meaning. It just makes the model more accurate in my case and what I do. I don't know how else to explain it physically. I just kind of think of it as polls just allow me to increase my resolution in modeling. That's how I think of it. That's not satisfactory. It's okay. Yeah. Yeah.
Do you change something in the code? Like you just change your transfer function in the code?
Yeah, you do. Yeah, you just change the transfer function in the code because it's all digital. So we just make an algorithm and then we just change the algorithm and we just say this is what I want now. That's it. Because the polls just basically tell the algorithm how the controller should behave. Because the algorithm doesn't know anything except that hey, we have a poll, we're adding a decay, or we're adding complex, or if it's a complex poll, we're adding oscillation and decay, and we can model everything off of decay or oscillation with decay or oscillation only. It's like amazing how like something that simple can be modeled by adding a sum of all of that. That's like what Fourier transform does too, is by I guess another way of thinking about it is, you know how in Fourier transform where you can basically model a square wave with an infinite sum of sines and cosines. To do that, you have to increase the number of poles. The more poles you have, the more accurate you can get this model of this, you know, whatever. I'm butchering this drawing. Um, and that's what adding poles and zeros do. But instead we're just adding it in code. That's it. Physical representation is kind of abstract when you go beyond second or third order systems. Yeah. Believe me, I've tried in the past to come up with a more intuitive way, and every year in my evaluations, people are like, "Can we, like, how? What does it mean?" And I'm like, I've been asking that myself for a while. If I could do it better, I would tell you, but I cannot. So, and maybe I'll jump ahead a little bit on like what you actually need to worry about when you're tuning PID and not what we do for school. So maybe that can put some of your concerns to rest. Anyway, so our lead controller is going to look like this, where we have K lead. I'm just going to use LD for shorthand notation, and we chose a 0 at 5 and a or -5, and we calculated our pole to be at -19.8. So this is our compensator. And I'm going to just stop a little bit early today because I want to show you a handout I have uploaded on Canvas about PID tuning. And I think it's just better to leave lag for next time to start it and finish it all in one go instead of starting halfway or starting and not finishing it until tomorrow. That awkward break is not very really conducive. So we're going to stop here for now. I'm going to go to Canvas and show you a little handout, and hopefully that'll also help put some of your like wonders and curiosity about what all of this actually means and why we don't actually use root locus on actual design. So this is more for the people who are interested in just PID tuning and are going to go to industry. So, oh, I already have it open. All right, so on under modules, I have this handout. I've had it since week 1, and maybe some people may finally understand what it is. It's called Tuning for PID Controllers PDF. And everything we did with root locus, you don't need. This is a pretty nifty handout about like this is just one tuning method, and it's like 15 pages long. And so this is what we learned from class. We add a pole, we have a pole at the origin, we have a 0 for the derivative part. So now you know what it is now. And what they tell you about root locus and Bode plots and traditional control methods are less appropriate if the system is unknown. So like this is the big thing. We use PID controllers on unknown systems. You can't use Bode plots. You can't use root locus. You can't use Bode plots. So they talk about how PID tuning is done on site right here. So then they have a few rules, which I find quite helpful. So first of all is you're just going to calculate, or not calculate, but test what the rise time is, or you need to determine the overshoot settling time and steady state error. And here they'll tell you what each component does when you increase the gain specifically. for each of these. So like KP is just proportional. There's no integral or derivative part. But let's say if we look at the derivative part, our rise time is not affected, so no definite trend. Overshoot could be decreased. Settling time is definitely decreased, and then steady state error, there's no trend. But then KI here, you can see our rise time is decreased, overshoot is increased, settling time is increased, probably something you notice in PID. And then steady state error is eliminated. So this is like a really nifty little graph that summarizes it. And then this is like a very common tuning method called the Ziegler-Nichols tuning rule. So I've actually used this before for tuning a PID controller. Instead of using root locus, I just use this method, and they just give you like these little steps where they're like, okay, this is like we measure our uncompensated response time for a certain K, and then you find this deflection point, and then from this, these are the gains you choose as a rough rule of thumb. And then you just play around with your gains until you get a response that you like. That's all it is, and they tell you how to find all of these, and they give you kind of like a standardized chart, and then you can tune each individual parameter until you get something that you like. But now the purpose of this class is to understand why we tune each gain. So why do we tune the integral gain? Why do we tune the derivative gain? Why do we tune the proportional gain? All of that is to make you understand what it does on the root locus, what it's doing mathematically. And now that you have that knowledge, you can just go back, and if you tune the derivative gain and guy comes up, or like your coworker comes up and says like, why are you tuning the derivative gain? You're saying like, I'm trying to reduce the settling time because that's what it does. Or why are you increasing the gain on your integral? And you tell them like, oh, the settling time's too long right now and the integral gain is too high. We'll reduce it, and that should reduce your settling time as well. So now that when they question you, you can now apply this tuning method and tell them why you know which gain to tune. And they just give you a general framework on how to tune the system, and really nice 15-page summary. It's not something you really need for this class, but something that might be useful for maybe future classes that they want you to just have a controller that stabilizes the system. You're like, I'll just throw a PID controller on there. And then usually what we do, like I guess in my line of research, we use like a stabilizing controller, and we throw on controllers on top of that. So we just need a controller that stabilizes a system, and then we throw on additional like loops on top of that, and all of that's done in algorithms, so in the computer. So it doesn't have any physical meaning. We're just telling how to add another controller to work with this controller in tandem. So it's a neat handout. Any questions? No. So in my line of work, so making a supercontroller, in my line of work, we just take an existing controller and we say, okay, it's stable, but it's not good performance wise. So then we design a controller for one specific performance metric. It can be very easy, and it is very easy for linear systems, but we're dealing with nonlinear systems. So that's where it makes it difficult. Adding linear controllers onto linear systems, even if you add more controllers on top, is easy. But it's when you deal with nonlinear controllers, the nonlinear system, that's when it gets complicated. Yeah, so this is actually the crux of like for industry PID controller tuning. You don't actually need root locus, but it's just to understand what it does. All right, so I'll see you all tomorrow.